All right, if you read through that section in 11.1 on Taylor polynomials, you will discover that you can find the polynomial to whatever degree they're asking for, and it turns out that it is the function at that spot plus the derivative at that spot, x minus the spot, then the second derivative at that spot over 2 factorial, which is 2, x minus a squared, and it keeps on going. This is actually going to be in the third derivative, x minus a cubed over 3 factorial, dot, 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 all the way out to the nth term, which would be the nth derivative at a over n factorial, x minus a to the n. And it looks a little weird, but if you go back to the first two terms, since the third term had a 2 factorial, and yet the second derivative and your x minus a was to the 2, that's the pattern. So on the second term, you're doing the first derivative, you're putting a 1 there over a 1 factorial, and then this guy is actually, he's f at a, no derivatives, and it's x minus a to the 0 over 0 factorial, and 0 factorial is 1. So that's how that comes about. So your general formula, all written out nice and they called it compactly, would actually be the summation for k equals 0 to n, and I don't like how they wrote it. Okay, I'm going to write it my way. The kth derivative at a over k factorial times x minus a to the k. And k goes 0, 1, 2, 3, 4, 5, and so on. So let's take a look at example 2. They want us to find the Taylor polynomials p's 1 through 7, really, centered at x equals 0 for sine of x. Okay, when it's centered at x equals 0, that means your a is 0. So it's going to make the problem much simpler. When a is 0, it actually has a special name. It's called a Maclaurin series when it is centered at 0. It's called a Taylor series when it's centered anywhere. And I'm going to set mine up a little bit different than the way the book did because I'm not quite sure I like how they organized it. The first thing you do is you take the function and you evaluate it at your center, and the sine of 0 is 0. Then you take the derivative, which is the cosine of x, at 0, and it's 1. Then the second derivative, which would be negative sine of x at 0, would be negative 1. The third derivative, that would be negative cosine of x at 0 would be, what did I write? Oops, this is 0. Shame on me. 0. This is negative 1. The fourth derivative, that's going to go back to sine of x. So now I'm starting over again. And if you take the derivative of sine, it takes 4 shots and it's back to its original state. So if you take a look at this, it's going to alternate 0, 1, 0, negative 1, 0, 1, 0, negative 1. And so now to write the Taylor polynomial, and they want it all the way out to 7. They want each and every one of these. Oh, this is just silly. Okay. So the polynomial at 1 is just going to be 0. There's nothing else to work with. And then we have, that's the function is 0, and then plus, then the first derivative is 1, x to the 1 over 1 factorial, so that just turns out to be x. P sub 2 is going to have f of x, so 0, plus the next guy, plus the second derivative, which is 0, x squared over 2 factorial. So this also is just x. If I go to P3, I'm going to have that 0 plus that x plus the next 0, and I'm going to write them out so that I can see what's happening here. Then I'm going to have the third derivative, which is negative 1, x to the 3 over 3 factorial. So if I simplify this, I actually just have x minus x cubed over 3 factorial. I could write it as x minus x cubed over 6. Either way is fine. So now at P4, P4 also has 0, so it's going to wipe out. So I'm just going to jump to P5. So P5, the first one is gone. Then we had the x. Then we had the minus x cubed over 3 factorial. Then we had a 0 for the fourth one. Then the fifth derivative is back to 1 again, x to the fifth over 5 factorial. If I went for P6, it's going to look exactly the same as that one, because the sixth one is going to be plus 0, x to the sixth over 6 factorial. And then finally, P7, and I'm going to write this one out from the very beginning to the end, because I think it might make more sense if you see the whole thing happen. So the first one is just f of x at 0. The second one is f prime at 0, 1, x to the 1 over 1 factorial. The next one is 0, that's the second derivative, x2 over 2 factorial. The next one is negative 1, x cubed over 3 factorial. The next one is 0, x to the fourth over 4 factorial. The fifth derivative is back to 1, x to the fifth over 5 factorial. The sixth one is 0, x to the sixth over 6 factorial. And the seventh one is negative 1, x to the seventh over 7 factorial. Cleaning this up, you end up with only odd terms. The other thing you need to notice about this is not only are they odd terms, but they are alternating in sign. So there's your Taylor or Maclaurin series for the sign of x. Now, they don't do it here in the book, but if you took the time here to graph each one of your answers, P1, what we're trying to do, and I'm going to do a rough sketch here, sine curve goes like this. And if you started graphing, and the first one is just y equals x, so it's just a line right here. So at 0, it's pretty accurate. But then the next one is a cubic function, and so it looks like this. It comes down, and I'm going to write on this. It's going to make a mess, but okay. Oops. No, it doesn't. It goes this way. And it's even better. And then if you graph up to the x to the fifth, it gets even better. And the more terms you add, if you actually type this into your calculator, it starts to look like the sine of x. And they do have a picture of it in the book for you. The more terms you put in there, the better it looks. The P sub 5 does some funky thing, and I wish I could change colors on here, but I can't. So let me draw a new sine curve. If you went and did all the way out to the seventh one, it follows it kind of. It goes like this. It looks like it's exact. And then it kind of veers off right here and goes a little underneath. And then it kind of gets weird. So it's going to keep on going at that point. And this is going to keep on going. But the more terms you take, the better it gets.